The second method for solving a linear system of two equations in two variables algebraically is called elimination. Now, we just learned substitution. The overall motivation for substitution is to take the two-equation, two-variable system and reduce it down into one equation in one variable. That's the same goal of elimination, but how we get there is just a little bit different. So let's go through the process. To solve a system of two linear equations in two variables using elimination, do the following. Number one, write both equations in general form, ax plus by equals c. Then number two, here's where sometimes you have to apply a little bit of thought and strategy. Multiply one or both equations by a non-zero constant to produce opposite coefficients. Now, opposite means opposite in sign. So if one equation has a coefficient of 2, I want the other equation to have a coefficient of -2. And this is for one variable in each equation. So again, multiply one or both equations by a non-zero constant to produce opposite coefficients for one variable in each equation. Now, once that's taken care of, I'm going to add the equations together term by term. Now remember, one of our variables will at this point have opposite coefficients. So when I add them together, they're going to cancel out. So this is going to yield an equation in one variable. So number 4, we're going to solve that resulting equation in one variable. And then number 5, once I have half the ordered pair, I'm going to back substitute this known value into either original equation and solve for the other variable. And finally, we'll express the solution as an ordered pair xy, and as always, check the answer in both original equations. So let's give elimination a try on example 2. Solve using elimination and express the solution as an ordered pair. So on example A, observe both of our equations are already in that general form, ax plus by equals c. So if you look at the equations vertically, the x's are lined up, the y's are lined up, and the constants are lined up together on the other side of the equal sign. So my goal is to multiply one or both equations by a number that's going to create opposite coefficients for one variable. And you can choose either variable. I'm going to choose to pick on x. Now, the reason I think x will be easy to eliminate is because in equation 2, x has a coefficient of 1. If you see a variable with a coefficient of 1, that's going to be the easiest one to eliminate. So I'm not going to make any changes in equation 1. I'm just going to copy it down. But I want to multiply equation 2 by a constant to create opposite coefficients for x. So in equation 1, the coefficient of x is 2. So I want the coefficient of x in the second equation to be -2. So I'm going to multiply every term in that equation by -2. This is going to give me -2x minus 16y, and don't forget about the other side. Multiply it by -2 as well. We get -4. And then we'll add our equations together term by term. So working vertically, notice we have 2x minus 2x. Those have opposite coefficients, therefore they cancel out and leave behind 0x. So we have eliminated one of the variables. Then we'll add the y's together. 6y plus -16y is -10y. And -1 plus -4 is -5. So notice we've achieved the same effect that we did with substitution. We eliminated one of the variables, so now we've arrived at a single equation in a single variable which we can solve. So I'm going to solve for y by dividing both sides by -10. -5 divided by -10 gives us 1/2. So there we have half of our solution. Remember, our solution is an ordered pair. So at this point, the rest of the method is very similar to what we did with substitution. I'm going to go back to one of the two original equations and solve for x. Now, I think that second equation looks a little simpler, so I'm going to use that one. But remember, you can use either equation. And I'm going to take the known information, that is y equals 1/2, and plug it into this equation. Again, that gives me another equation in a single variable. So 8 times 1/2 is 4. I can solve for x by subtracting 4 from both sides, and it looks like our x value is -2. So we're going to put this together in an ordered pair. X has to come first, so -2 is first, and y is second. So it looks like our ordered pair solution is -2 1/2. but we want to be sure, so we're going to check by substitution. So my first equation was 2x plus 6y equals negative 1. And we're going to replace x with negative 2 and y with 1/2. And check to see if we have a balanced equation. So on the left side, we have negative 4 plus 3, and clearly that's equal to negative 1. So negative 1 on the left, negative 1 on the right, we have a balanced equation. Now, that's a good sign, but we want to make sure it works in both original equations. So let's take a look at our second equation, x plus 8y equals 2. We'll replace x with negative 2, and we'll replace y with 1/2, and check for balance. So on the left side, we have negative 2 plus 4, and that gives me a balanced equation. So we can be absolutely confident that our ordered pair is the solution to the system. And once again, graphically, this means that the two lines described by those two original equations would intersect in the ordered pair negative 2, 1/2. Okay, let's try another one. On example B, this one's different for a couple of reasons. The first is that both of those equations are not in general form. So to begin with, we need to rearrange them in general form. And remember, general form is ax plus by equals c. So in that first equation, we need to subtract 3y from both sides. So the new first equation would be 2x minus 3y equals 9. And in the second equation, we need to add 3x to both sides. So this would give us 3x plus 4y equals 5. Now we need to figure out how to eliminate one of the variables. This one's less convenient than our previous example, because remember, our previous example contained a variable with a coefficient of 1. X and y all have coefficients not equal to 1 in both of these equations. So you can choose to eliminate either variable. You can eliminate x or you can eliminate y. I'm just going to arbitrarily choose to eliminate x. So my goal is to obtain opposite coefficients for x. The coefficient of x in equation 1 is 2, and the coefficient of x in equation 2 is equal to 3. So what I'm going to do is basically switch these two coefficients as multiples and change the sign of one of them. So I'm going to multiply equation 1 all the way through by negative 3. I'm going to do that on both sides. Now think about what that will do for x. Multiplying 2x by negative 3 is going to give me a negative 6x term there. So I want to get a positive 6x term in the second equation. To get a positive 6x term, I'm going to have to multiply it by 2. But what I do to one term, I'm going to have to do to all of the terms. So let's go ahead and apply those multiples throughout the equations. So looking at equation 1 there, distributing the negative 3 to all terms of the equation, that's going to give us negative 6x plus 9y equals negative 27. And then distributing 2 throughout the second equation, we get 6x plus 8y. Don't forget about the right side. We're multiplying that by 2 as well, so we get 10. And look what we've achieved. X now has opposite coefficients, a negative 6 and a positive 6 in those equations. So when I add them together, the x's are going to cancel. And we're going to end up with an equation in one variable. 9y plus 8y gives me 17y. Negative 27 plus 10 gives me negative 17. We can solve for y by dividing both sides by 17, and it looks like the y coordinate of our solution is negative 1. Now we can use back substitution to find the value of one of the other variables. I'm going to go back to the original equation 1, which almost has x isolated, but not quite. But I'm going to use that one. You can use either equation to figure out x. We're going to take what we know about y and plug it into this equation, and we'll be able to solve for x. So on the right side here, we'll have 9 plus 3 times negative 1. That's 9 minus 3, or 6. And then divide both sides by 2, and the x coordinate of our solution is 3. So our proposed ordered pair solution would be x equals 3 and y equals negative 1. And we're going to be diligent and check by substitution. Now I'm going to check this ordered pair in the original equations, just in case I made some kind of silly mistake in a subsequent step in my process. So I'm going all the way back to the original. So my first equation was 2x equals 9 plus 3y. So I'm going to replace x with 3 and y with -1, and we want to know, is that a balanced equation? So on the left side we have a 6. On the right side we have 9 minus 3, which is also 6. So that's a good sign, but let's check it in the second equation to be sure. We have 4y equals 5 minus 3x. We're going to replace y with -1, and we're going to replace x with 3. On the left side we have -4. On the right side we have 5 minus 9, which also gives me -4. So this ordered pair balances both equations. Therefore, it is the solution to the system. And once again, this means that if I were to graph those two lines, they would intersect in the ordered pair 3, -1. So at this point, we have two algebraic methods for solving systems. The first one is called substitution, and the second one is called elimination. Next, we'll look at a matrix method for solving systems.